Hello everyone. Last class we studied conditional probability, which says let A and B be two events with probability of B not equal to 0. The conditional probability of A given occurrence of event B is defined as probability of A given B equal to probability of A intersection B over probability of B. That's what we learned last class. Today, let me show you more about conditional probabilities. First of all, let me show you a theorem. For all events A, B, and C, first one, probability of A complement given B equal to 1 minus probability of A given B. Next, probability of A intersection B can be rewritten as probability of A times probability of B given A, or probability of A intersection B can be rewritten as probability of B times probability of A given B. These two formulas have a name. These two formulas have a name. They are called the multiplication rule. These two formulas has a name. They are called the multiplication rule of probabilities. We can write intersection as a product. So they are called the multiplication rule of probabilities. Next, probability of A intersection B intersection C can be rewritten as probability of A times probability of B given A times probability of C given A intersection B. Let's prove it. So let's prove the first one first. We try to prove that the left side equal to the right side. So let's start from the left side. Probability of A complement given B that can be rewritten as probability of A complement intersection B over probability of B. That's the definition of conditional probability. Probability of A given B is probability of A intersection B over probability of B. That's the definition of conditional probability. Then the numerator, A complement intersection B, that can be rewritten as what? Look at the picture. Assume that's set A. Assume that's set B. A complement intersection B that represents everything in B but not in A. This region here is A complement intersection B. A complement intersection B represents everything in B but not in A. So the shaded region here represents the set A complement intersection B. This can be rewritten as probability of B take away A intersection B. Probability of B take away the probability of A intersection B. The entire set B take away the intersection here. So the numerator can be rewritten as probability of B minus probability of A intersection B. Over probability of B. Then this can be rewritten as probability of B over probability of B minus probability of A intersection B over probability of B. The first term, probability of B over probability of B is 1. The second term, probability of A intersection B over probability of B. By definition of conditional probability. This is probability of A given B. So that's the proof of the first statement. That's the proof of the first statement. Next, the second statement of the theorem is called the replication rule, or the product rule of probabilities. Let's prove it. First equation says probability of A intersection B equal to probability of A times probability of B given A. Let's try to prove the right side equal to the left side. Let's try to prove the right side equal to the left side. So for the first equation, the left side is probability of A times probability of B given A. By the definition of conditional probability, this probability can be rewritten as probability of A intersection B over probability of A. Take intersection, divide by the condition. Here the condition is the second part. Here A is the condition. So take A intersection B divided by probability of A. Then cancel probability of A. We get probability of A intersection B. That's the proof of the first equation. The second equation is very similar. We try to prove the right side equal to the left side. Probability of B times probability of A given B. Let's rewrite the conditional probability first. The conditional probability A given B, that can be rewritten as probability of A intersection B. Take intersection first, then divide by the condition. Condition is always the second part. The part on the back is always the condition. A is the first part is what we are looking for. The second part is the condition. So take an intersection, divide by the condition. Condition is probability of B. Then we can cancel probability of B. What's left is probability of A intersection B. So here we show that the right side equal to the left side. So that's the proof of the second statement. The third statement. Third statement says probability of A intersection B intersection C equal to probability of A times probability of B given A times probability of C given A intersection B. So let's prove it. Here, the right side looks more complicated. So we try to show the right side equal to the left side. Since the right side looks more complicated, we try to show the right side equal to the left side. This is a replication rule for 3 events. This equation is called a replication rule for 3 events. So let's try to show the right side equal to the left side. The right side is probability of A times probability of B given A times probability of C given A intersection B. Probability of A stays the same. Probability of B given A can be rewritten as probability of A intersection B over the condition, over the probability of the condition. Here A is a condition, so divide by probability of A. Next, use definition of conditional probability, rewrite this probability. It can be rewritten as the intersection A intersection B intersection C. Take intersection first, then divide by the condition. The second part is a condition. Divided by probability of A intersection B. Then here we can cancel probability of A. Cancel probability of A intersection B. What's left is probability of A intersection B intersection C. Here in the theorem, the second and the third statement, they are called replication rules of probabilities. In the second statement, we can write the intersection of 2 events as a product of 2 simpler probabilities. And in the third statement, we can write the intersection of 3 events as a product of 3 simpler probabilities. Next, let's look at an example. In a college, there are 3 calculus classes, calculus 1, calculus 2, and calculus 3. An academic survey shows that 35% of their students pass calculus 1. For those who pass calculus 1, 80% of them pass calculus 2. And for those who pass both calculus 1 and calculus 2, 75% of them pass calculus 3. when a student in a school is asked randomly, find each of the following probabilities. Part A. If it's known that he passed calculus 1, what's the probability that he did not pass calculus 2? So let's set down a problem first. Let event A represent a student pass calculus 1. Let event A represent the student pass calculus 1. Let event B represent that the student pass calculus 2. Let event C represent that the student pass calculus 3. Now write down what's given. 35% of the students pass calculus 1. So probability of A is 35%. For those who pass calculus 1, 80% of them pass calculus 2. So if a student pass calculus 1, the chance he also pass calculus 2 is 80%. For those who pass calculus 1, the chance he pass calculus 2 is 80%. That's what's given here. For those who pass calculus 1, 80% of them pass calculus 2. And for those who pass both calculus 1 and calculus 2, for those who pass calculus 1 and calculus 2, 75% of them pass calculus 3. So for those who pass calculus 1 and calculus 2, the chance he pass calculus 3 is 75%. For those who pass calculus 1 and calculus 2, the chance he pass calculus 3 is 75%. That's what's given in the problem. Now, first question. The problem is asking if it's known that he passed calculus 1. If it's known that the student passed calculus 1, what's the probability that he did not pass calculus 2? B represents the student passed calculus 2. So if the student did not pass calculus 2, we use B complement. B complement represents the student did not pass calculus 2. So that's what we are looking for. If the student passed calculus 1, what's the probability that he did not pass calculus 2? Then use the formula. Use the formula from the previous theorem. Probability of B complement given A can be rewritten as 1 minus probability of B given A. Using the previous formula. The first formula in the previous theorem. Probability of A complement given B is 1 minus probability of A given B. So the condition stays the same. A complement become A. 1 minus probability of A given B. Condition stays the same. Probability of A complement given B is 1 minus probability of A given B. Condition stays the same. And the probability is the complement. Condition stays the same. The probability what we are looking for is a complement here. So probability of B complement given A is 1 minus probability of B given A. Then plugging numbers. Probability of B given A is 80%. It's 0.80. 1 minus 0.80 is 0.20. That means for those who pass calculus 1, the chance he did not pass calculus 2 is 20%. For those who pass calculus 1, the chance he will pass calculus 2 is 80%. And the chance he will not pass calculus 2 is 20%, 0.20. That's part A. Part B. What's the probability that this student pass both calculus 1 and calculus 2? So this problem is asking probability of A intersection B. Probability that the student pass calculus 1 and calculus 2. Now, for probability of A intersection B, if we use replication rule, there are two ways to run the formula. We can write it either as A probability of A times probability of B given A, or we can write it as probability of B times probability of A given B. Which formula should we use? Here, look at event A and B. Which event comes first? Event A represents the student pass calculus 1. Event B represents the student pass calculus 2. Which event comes first? We know that event A comes first. The student must pass calculus 1 first, then pass calculus 2. This event comes first. So since event A comes first, we write probability of event A first, then times probability of B given A. Since event A comes first, we write probability of A first, then times probability of B given A. Use this formula since the event A comes first. Then probability of event A, the chance that a student pass calculus 1 is 0.35. Times probability of B given A. If the student passes calculus 1, the chance he passes calculus 2 is 80%, 0.80. If the student passes calculus 1, the chance that he passes calculus 2 is 0.80. Multiply 0.35 and 0.80. Here I use my calculator, I get 0.28. Part C. What's the probability that the student passes all 3 calculus classes? What's the probability that this student passes all 3 calculus classes? What's the probability that this student passes all 3 calculus classes? So what we are looking for is probability that this student passes calculus 1, calculus 2, and calculus 3. Use replication rule, the third formula. This formula can be rewritten as probability of A times probability of B given A times probability of C given A intersection B. That's the multiplication rule for the intersection of 3 events. Then plug in. Probability of A is 0.35. The chance that student pass calculus 1 is 35%. Then probability of B given A, if he passes calculus 1, the chance he passes calculus 2 is 80%. Times probability of C given A intersection B. If the student passes both calculus 1 and calculus 2, the chance he passes calculus 3 is 75%. Then multiply 0.35 and 0.80 and 0.75. Here I use my calculator, I get 0.21. That's the chance that a student pass all 3 calculus classes. Next, let me introduce the law of total probability. The law of total probability. Let B1, B2, Bn mutually exclusive events. Let B1, B2, Bn mutually exclusive events. And B1 union B2 union Bn. The union of this event together is a sample space. Let B1, B2, Bn mutually exclusive events. And the unions, their unions, B1 union B2 union Bn is a sample space. Let A be an event in a sample space. A be an event in a simple space. Here, let me show you the picture first. Assume this rectangle is a simple space S. Assume this rectangle represents a simple space S. Assume this set here is B1. Assume this set is B2. Continue. Assume that's BI. Assume that's BI. And the last one is BN. B1, B2, let me write B3 here. Assume that's B3, let's set B3. And so on. That's BI, and the last one is BN. Assume B1, B2, BN, they are M mutually exclusive events. Means for this event, they have nothing in common. They are all disjoint events. They have nothing in common. And the union of the B's, if I combine all these set together, I get a simple space. The union of this B1, B2, B3, Bn together is a simple space. Let A be an event in a simple space. Let A be an event in a simple space. Then A may intersect B1, B2, B3, Bi, Bn. Set A may intersect these sets here. It's possible that set A will intersect B1, B2, B3, Bi, Bn. Assume this is set A. Assume this is set A. Then set A can be rewritten as probability of A can be rewritten as this set plus this set plus this and plus this. So set A can be rewritten as probability of B1 intersection A. This is B1 intersection A plus probability of B2 intersection A. This is B2 intersection A. Plus, in general, plus the last one, Bn intersection A. So here we can see that B1 intersection A plus B2 intersection A plus B3 intersection A plus Bn intersection A. Together we get set A. This is B1 intersection A. This is B2 intersection A. This is B3 intersection A. This is Bi intersection A. This is Bn intersection A. All together, we get set A. That's probability of set A. Then, if I use multiplication rule here, the first probability can be rewritten as probability of B1 times probability of A given B1. If I use multiplication rule here, the first probability can be rewritten as probability of B1 times probability of A given B1. The second probability can be rewritten as probability of B2 times probability of A given B2. And rewrite all the probabilities. Rewrite every probability using the same format. The last one will be probability of Bn. The last one will be probability of Bn times probability of A given Bn. So this formula can be rewritten as probability of A equal to probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2 plus probability of Bn times probability of A given Bn. This formula is called the law of total probability. This formula is called the law of total probability. This formula is called the law of total probability. Sometimes we can write this formula using sigma notation. Sometimes we can write this formula using sigma notation. Using sigma notation, this can be written as probability of A equal to the sum I from 1 to n, probability of Bi times probability of A given Bi. This formula is called the law of total probability. We can use either the first formula or the second formula. Second formula looks simpler. If we use sigma notation, it looks simpler. We can use either the first formula or the second formula. They are equivalent. They are exactly the same formulas. This formula is called the law of total probability. Next, let k be an integer. Let k be an integer with k between 1 and n. So let k be an integer between 1 and n. Then, how do we find probability of bk given a? How do we find probability of bk given a? Probability of bk over a, this is a conditional probability. If we use a formula, it can be rewritten as probability of A intersection bk. Let's write bk intersection A first. That's probability of bk intersection A over probability of A. The second part is always a condition. Put it on the bottom. So that's probability of bk intersection A over probability of A. For the numerator, if I use replication rule, it can be rewritten as probability of bk times probability of A given bk. If I use replication rule, the numerator can be rewritten as bk times probability of A given bk. The denominator is probability of A. Probability of A, if I use law of total probability, they equal to this. The denominator probability of A, if I use law of total probability, they equal to this. Equal to this. So, probability of bk given A that equal to probability of bk times probability of A given bk over probability of A. Here I use law of total probability. Rewrite the button using this. That's probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2 plus the last one, until the last one, Bn times probability of A given Bn. If I use conditional probability and the law of total probability together, this formula also have a name. This formula is called the Bayes theorem. This formula is called the Bayes theorem or Bayes formula. This formula is called the Bayes theorem or the Bayes formula. B-A-Y-E, Bayes formula. This formula is called the Bayes formula, B-A-Y-E, Bayes formula. This formula is called the Bayes formula, B-A-Y-E, the Bayes formula. If I apply conditional probability and the law of total probability together, this formula is called the Bayes formula. Here, let me rewrite the law of total probability and the Bayes formula in a different page. Probability of A is probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2 plus probability of Bn times probability of A given Bn. This formula is called the law of total probability. It can be rewritten in sigma notation. So in sigma notation, probability of A equal to the sigma I from 1 to n, probability of Bi times probability of A given Bi. This formula is called the law of total probability. For the Bayes formula, if we combine the law of total probability and conditional probability together, that's the formula for Bayes theorem. I can also put the denominator in the form of sigma notation. So these two formulas, they are called the Bayes formula. These two formulas, they are called the law of total probability. Memorize both formulas. Next, let's do an example. Let's do an example here. At a hospital's emergency room, patients are classified. 20% of them are critical, 30% are serious, 50% are stable. Of the critical ones, 40% die. Of the serious, 10% die. Of the stable, 1% die. When a patient is sent to the emergency room, what's the probability the patient die later? That's part A. When a patient is sent to the emergency room, what's the probability that the patient die later? Part B. If a patient died in the emergency room, what's the probability that the patient was classified as critical? So let's set down the problem first. First of all, let's translate everything. The A represents a patient is classified as critical. A patient is classified as critical. The B represents a patient is classified as serious. The C represents a patient is classified as stable. The D represents a patient die. The D represents a patient die in the emergency room. Now let's write down the given information. 20% of them are critical. So the chance that a patient is critical is 20%. 20% of the patient in the emergency room is critical. 20% patient in the emergency room is classified as critical. 30% of them are serious. So the chance that a patient is serious is 30%. 50% of them are stable. So if a patient is stable, the chance is 50%. The probability that a patient is stable is 50%. That's what's given. Of the critical ones, 40% die. If a patient is classified as critical, the chance he die is 40%. This is condition. If a patient is classified as critical, the chance he die is 40%. Of the series 10% die. Of the series, 10% die. So if a patient is classified as serious, the chance he die is 10%. If a patient is classified as serious, the chance he dies is 10%. Of the stable, 1% die. So if a patient is classified as stable, the chance he dies is 1%. If a patient is classified as stable, the chance he dies is 1%. That's what's given. Part A. What we are looking for is, if a patient is sent to an emergency room, what's the probability that the patient dies later? So in part A, what we are looking for is the chance that the patient dies in the emergency room. That's what we are looking for in part A. If a patient is sent to an emergency room, what's the probability that the patient dies later? That's what we are looking for. Probability that a patient dies in the emergency room. That's what we are looking for. So here we can use the law of total probability. If a patient dies in the emergency room, this patient may be classified as critical, then he dies later. This patient may be classified as serious, then he dies later. This patient may be classified as stable, then he dies later. Then we can use replication rule to rewrite each probability here. Probability of A intersection D can be rewrite as probability of A times probability of D given A. Probability of B intersection D can be rewrite as probability of D times probability of D given B. Probability of C intersection D can be rewrite as probability of C times probability of D given C. Then plug in the numbers. Probability of A is 20%. Probability of D given A is 40%. Probability of B is 30%. Probability of D given B is 10%. Probability of C is 0.50, is 50%. Probability of D given C is 1%, that's 0.01. Then multiply, we get 0.08 plus 0.03 plus 0.005. Adding up, we get 0.115. That's the chance that a patient dies in the emergency room. That's the chance that a patient dies in the emergency room. That's part A. Part B. If a patient died in the emergency room, what's the probability that the patient was classified as critical? Part B. If a patient died in the emergency room, that's a condition. The patient died in the emergency room. What's the probability that the patient was classified as critical? Even A represents a patient is classified as critical. So what we are looking for is probability of A, given he died in the emergency room. What we are looking for is probability of A, given that he died in the emergency room. Then this is conditional probability. Use the formula for conditional probability. We have probability of A intersection D over probability of D. The denominator is a condition. Then the numerator, probability of A intersection D, we can use replication rule to rewrite the numerator. Probability of A intersection D can be rewrite as probability of A times probability of D given A. Denominator stays the same. Then we can plug in numbers. In the numerator, probability of A is 20%. Times probability of D given A. Probability of D given A is 0.40, it's 40%. Over probability of D. From part A, we know that probability of D is 0.115. Then multiply, we get 0.08 over 0.115. If I use my calculator, I get 16 over 23. So if a patient died in the emergency room, the chance that he was classified as critical is 16 over 23. Next example. Assume 2% of the population has a particular disease. A test will detect a person with the disease 90% of the time. However, it will say that a person without the disease has the disease about 5% of the time. Now a person is randomly selected from the population and take the test. Part A. If the test indicates that this person has a disease, what's the probability that he actually has a disease? So for this problem, let's first of all set down the problem, translate first. So let D represent a person has disease. A person has the particular disease. Let D represent a person has a particular disease. Let plus represent a person is test positive. Let plus sign represent a person is test positive. That means the test says this person has disease. If a person is test positive, that means the test says this person has disease. Let minus represent a person is test negative. If a person is test negative, that means the test says this person doesn't have the disease. If a person is test negative, that means the test says this person doesn't have the disease. So let's write down what's given. Assume 2% of the population has a particular disease. That means probability that a person has disease in the population, a person has disease is 2%, which is 0.02. That's what's given. A test will detect a person with the disease 90% of the time. That means, what does this mean? That means if a person has a disease, the test will say this person has disease 90% of the time. If a person has a disease, he will be test positive 90% of the time. That's what this statement says. A test will detect a person with a disease 90% of the time. If a person has a disease, and the chance he will test positive is 90%. However, it will say that a person without disease has a disease about 5% of the time. That means if a person doesn't have a disease, the test will say the person has a disease 5% of the time. If a person doesn't have a disease, the chance will say this person has disease 5% of the time. That's what's given. Now part A, what we're looking for is that if the test indicates that this person has a disease, what's the probability that this person actually has a disease? If the test indicates that this person has disease, means this person tests positive. If the test indicates that this person has disease, then this person will be test positive. What's the probability that he actually has a disease? So if the test is positive, what's the probability that he actually has a disease? This is conditional probability. If we use a formula for conditional probability, this can be rewritten as probability D intersection positive over probability of positive. This is condition. Condition go to the denominator. Intersection go to the numerator. Then use replication rule. The numerator can be rewritten as The numerator can be rewritten as probability that the person has disease times probability that the test is positive given he has disease. Rewrite the numerator using replication rule. And for the denominator, use law of total probability. For the denominator, use law of total probability. If a person is test positive, it's possible that he has disease, then test positive. Or there's a small chance that he doesn't have a disease, but still test positive. So, if a patient is test positive, there are two cases. Either he has disease and then test positive, or there's a small chance that he doesn't have a disease, but still tests positive. Then, rewrite the denominator. Rewrite the denominator using replication rule. We have probability of D times probability of plus given D plus probability of D complement times probability of plus given D complement. Keep numerator the same. Then plug in numbers. Probability that the patient has disease is 0.02. Probability that given the patient has disease, the chance that he test is positive is 90%. Then the denominator, probability of D is 0.02. Given that the person has disease, the chance that he tests positive is 90%. Plus probability of D complement. Since probability of D is 0.02, probability of D complement is 1 minus probability of D, which is 0.98. And given that the person doesn't have disease, the chance that the test is positive is 0.05. Then use calculator for the rest. Use calculator to get an answer. Here in part A, I use my calculator, I get 18/67. Part B, if the test indicates that this person doesn't have a disease, what's the probability that he actually doesn't have the disease? So part B, if the test indicates that this person doesn't have a disease, that means this person is test negative. If the test indicates that this person doesn't have disease, then that means he will be test negative. What's the probability that he actually doesn't have the disease? It's D complement. He actually doesn't have the disease is D complement. If he's test negative, what's the probability that he doesn't have a disease? So this is conditional probability. Use the formula. It can be rewritten as probability of D complement intersection minus over probability of minus. Now, if this person is test negative, there are two cases. Either he has disease, then he's test negative, or he doesn't have disease and he tests negative. There are two cases. Either he has a disease and tests negative, or he doesn't have disease and tests negative. Keep the numerator the same. Then rewrite everything here. Rewrite every probability using replication rule. The numerator can be rewritten as probability of D complement times probability of minus given D complement. The denominator can be rewritten as probability of D times probability of minus given D plus probability of D complement times probability of minus given D complement. Let's try to plug in the numbers. What's the probability that the person doesn't have a disease? We know that in the population, 2% of them have disease. That means the chance that a person doesn't have disease is 98%. That's 0.98. If the person doesn't have disease, what's the chance the person is test negative? If a person doesn't have disease, what's the probability that this person is test negative? We know that if a person doesn't have disease, the chance he tests positive is 0.05. If a person doesn't have disease, the chance he tests positive is 0.05. That means if this person doesn't have disease, the chance that he tests negative is 0.95. If a person doesn't have disease, the chance that he tests positive is 0.05. That means if this person doesn't have disease, the chance he tests negative is 0.95. It's an opposite. So if this person doesn't have disease, the chance that he tests negative is 0.95. On the denominator, the chance that a person has disease is 0.02. If the person has disease, the chance that he tests negative, what's that? We know that if person has disease, the chance that he tests positive is 90%. That means if this person has disease, the chance that he will be test negative is an opposite, which is 10%. If a person has disease, the chance he tests positive is 90%. That means for the same person, he will be test negative. The chance he will be test negative is 10%. This is the opposite of this. Plus probability of D complement is 98%. Plus probability of negative given D complement. If a person doesn't have disease, the chance he will be test negative is 0.95. Here, using my calculator, I get 931 over 933. That means if the test indicates this patient doesn't have disease, the chance that he actually doesn't have disease is 931 over 933. Next, let me introduce independent events. Events A and B are said to be independent if probability of A intersection B equal to probability of A times probability of B. Let me first of all show you an example. When a die is rolled twice, let A be an event that the first row come up a 1. The first row come up a 1. And let B be the event that the second row come up a 2. determine whether events A and B are independent. So let's find probability of A and B first, and then determine whether they are independent. How do we find probability of A? Remember, probability is always the number of favorable outcomes divided by the number of all possible outcomes. Let's find the number of all possible outcomes first. When we roll two dice, a die has 6 outcomes. So when we roll 2 dice, we have 36 different outcomes. 6 times 6 is 36. That's the number of all possible outcomes. Now, the numerator is the number of favorable outcomes. Event A is the event that the first die comes up 1. We only care about the first die. The second die could be any numbers. So if the first die comes up 1, there's only one way. There's only one way to obtain a 1 from the first die. For the second die, it could be any one of the 6 numbers. It could be 1, 2, 3, 4, 5, 6. So we have 6 choices for the second die. For the first die, since it must be 1, there's only one choice. For the second die, it could be any one of the 6 numbers. So there are 6 choices for the second die. Together, that's 6 over 36, which can be simplified as 1 over 6. How about probability of B? Probability of B is the event that the second row comes up 2. So probability is always number of favorable outcomes divided by number of all possible outcomes. Number of all possible outcomes is 6 squared. When we roll 2 dice, each die has 6 outcomes. When we roll a die twice, every row has 6 different outcomes. Together is 6 squared. So that's the number of all possible outcomes. For the number of favorable outcomes, the second row comes up 2. So the first row could be any number. We don't care about the first row. All we care is the second row. Second row must be a 2. So from the first row, there are 6 choices. It could be any one of the 6 numbers. From the second row, it must come up 2. 2 is one of the 6 numbers. There's only one way to obtain 2. 2 is one of the 6 numbers. There's only one way to obtain 2. So together it's 6 over 36, which is 1 over 6. That's probability of A and probability of B. Next, we try to verify if probability of A intersection B equal to probability of A times probability of B. So let's try to find probability of A intersection B. For A intersection B, we need to consider both event A and B. So keep in mind that probability is always number of favorable outcomes divided by number of all possible outcomes. When we roll 2 dice, the denominator is 6 squared. Each die has 6 outcomes. Together we have 36 different outcomes. For the numerator, event A says the first row comes up 1. Event B says the second row comes up 2. So if the first row is 1, there's only one choice. There's only one way to obtain a 1. Second row comes up 2. There's only one way to obtain a 2. Together we get 1 over 36. Then let's verify. What's probability of A times probability of B? Probability of A times probability of B is 1 over 6 times 1 over 6, which is 1 over 36, which is exactly the same as probability of A intersection B. So, since probability of A intersection B equal to probability of A times probability of B, then events A and B are independent. In general, if 2 events they won't affect each other, we say they are independent events. Here, when we roll the die, when we roll the die twice, in the first row and the second row, the result in the first row won't affect the result in the second row. So here we can say that they are independent events. If 2 events they won't affect each other, we can say that they are independent events. When we roll the first die, whatever the result is, it won't affect the result of the second die. So they're independent events. If the events, they won't affect each other, they are independent events. Next example, let A and B be two events. If probability of A equal to 0.8, probability of B equal to 0.5, and probability of A intersection B equal to 0.9, are A and B independent events? Are A and B independent events? Let A and B be two events. If probability of A is 0.8, probability of B is 0.5, and probability of A intersection B is 0.9, are A and B independent events? So try to verify that. If A, B are independent, that means probability of A times probability of B equal to probability of A intersection B. If A and B are independent, probability of A times probability of B must be probability of A intersection B. Let's verify. What's probability of A times probability of B? In this example, probability of A times probability of B is 0.8 times 0.5, which is 0.4. And that's not the same as 0.9. Since probability of A times probability of B is not the same as probability of A intersection B, then events A and B, they are not independent events. Next example, let A and B be independent events with probability of A is 1 over 4 and probability of B is 2 over 3. Find each of the following probabilities. Part A, probability of A intersection B. For probability of A intersection B, since A and B are independent events, A intersection B is the same as probability of A times probability of B. Then plug in probability of A and B. Probability of A is 1 over 4. Probability of B is 2 over 3. If we multiply, we get 1 over 6. That's probability of A intersection B. Part B. What's probability of A union B? Probability of A union B can be found using the formula. That's equal to probability of A plus probability of B minus probability of A intersection B. Then plug in the numbers. Probability of A is 1 over 4. Probability of B is 2 over 3. Minus probability of A intersection B, which is 1 over 6. Then use calculator. Here I got 3 over 4. Part C. Probability of A complement intersection B complement. For A complement intersection B complement, we can use De Morgan's law first. That can be rewritten as probability of A union B complement. A union B complement can be rewritten as probability of 1 minus probability of A union B. And we know that A union B from part B here, A union B is 3 over 4. 1 minus 3 over 4 is 1 over 4. That's part C. Part D. Probability of A intersection B complement. For probability of A intersection B complement, we can draw a Venn diagram. Assume this is set A, this is set B. A intersection B complement represents everything in A but not in B, as in this region here. That can be rewritten as probability of A take away probability of A intersection B probability of A, take away probability of A intersection B. Probability of A is 1 over 4. A intersection B from part A, probability of A intersection B is 1 over 6. 1 over 4 minus 1 over 6 is 1 over 12. Next example, a bag contains 3 blue marbles, 4 green marbles, and 5 red marbles. When 2 marbles are randomly selected from the bag, let A be the event that the first marble is blue. Let B be the event that the second marble is green. Determine whether events A and B are independent. So, in order to determine if they are independent or not, we try to verify this formula. If probability of A times probability of B equal to probability of A intersection B, then events A and B are independent. So let's find probability of A and B first. What's probability of A? Remember, probability is always number of favorable outcomes divided by the number of all possible outcomes. We can try to find the number of all possible outcomes first. There are totally 3 blue marble, 4 green marble, and 5 red marble. 3 blue, 4 green, 5 red. Together we have 12 marbles. We are choosing 2 marbles randomly from the bag. Doesn't order matters. Doesn't order matters. In part A, event A. Event A represents A is the event that the first marble is blue. B is the event that the second marble is green. Since we specify the first one, second one, third one, that means the order matters. Since we specify the first marble, second marble, third marble, that means we care about the order. The order matters. If the order matters, we use permutation. If the order doesn't matter, we use combination. If the order matters, we use permutation. So, for denominator, we are choosing 2 marble out of 12. And we're doing permutation, order matters. It's permutation 12 choose 2. For the numerator, event A represents that A is the event that first marble is blue. We only care about the first marble. First marble must be blue. So for event A, we choose a blue marble out of 3. For the first marble, we choose a blue marble out of 3. It's permutation 3 choose 1. Order matters. Permutation 3 choose 1. We choose 1 blue marble out of 3. Now for the second marble, since we only care about the first marble, second marble, it may or may not be blue. We don't care. It may or may not be blue. I pick 1 blue marble from here. And there are 2 blue marbles left. Together, we still have 11 marbles. Since I pick 1 blue marble in the first place, there are 11 marbles left. And the second marble could be any color. We don't care about the color. So for the second marble, we choose 1 marble out of the remaining marble, which is permutation 11 choose 1. Then use your calculator. Permutation 3 choose 1 is 3. 11 choose 1 is 11. 12 choose 2 is 12 times 11. Cancel 11, we got 3 over 12, which is 1/4. So the chance that the first marble is blue, is 1 over 4. Next, let's compute probability of event B. Probability is always the number of favorable outcomes divided by the number of all possible outcomes. We can find the number of all possible outcomes first. We are choosing 2 marbles out of 12. That's permutation 12 choose 2. Order matters. We use permutation. Permutation 12 choose 2. That's the denominator. For the numerator, that's the number of favorable outcomes. What we want is the second marble is green. We don't care about the first marble. All we care is the second marble must be green. So let's make choice for the second marble first. So here, let's choose the second marble first. If we make choice for the second marble, we must choose a green marble. So we choose 1 green marble out of 4, and we use permutation. Permutation 4 choose 1. We choose a green marble out of 4. That's for the second marble. For the first marble, we don't care about the color. It could be any colors. Since I only pick 1 green marble from here, there are 3 green marbles left. Together we have 11 marbles. So for the first marble, we choose 1 marble out of 11. That's permutation 11 choose 1. So permutation 4 choose 1 is 4. 11 choose 1 is 11. 12 choose 2 is 12 times 11. Cancel 11, we get 4 over 12. 4 over 12 can be reduced as 1 over 3. If we multiply probability of A times probability of B, if we multiply probability of A times probability of B, that's 1 over 12. If we multiply 1 over 4 times 1 over 3 is 1 over 12. Next, we try to compute probability of A intersection B. For probability of A intersection B, we must consider both event A and B. Probability is always number of available outcomes divided by number of all possible outcomes. We can find the denominator first. Let's find the number of all possible outcomes first. There are totally 12 marbles. We are choosing 2 marbles out of 12. That's permutation 12 choose 2, since order matters. Permutation 12 choose 2. For the numerator, we need to consider both event A and B. First marble must be blue, and the second marble must be green. For the first marble, we are choosing 1 blue marble out of 3. That's permutation 3 choose 1. For the second marble, we choose 1 green marble out of 4. That's permutation 4 choose 1. Then use calculator. Permutation 3 choose 1 is 3. Permutation 4 choose 1 is 4. Permutation 12 choose 2 is 12 times 11. If we simplify here, 3 times 4 is 12. Cancel 12 from top and bottom, I get 1 over 11. And here we can see that probability of A intersection B is not the same as probability of A times probability of B. Probability of A intersection B is not the same as probability of A times probability of B. So A and B are dependent, they are not independent. So events A and B are not independent. In general, if 2 events they are not independent, that means they will affect each other. One of the event will affect the other event. Let me show you a picture. We'll see how they affect each other. Let me show you a picture. We'll see how they affect each other. Consider in a box, in a bag. Consider in a bag. There are 3 blue marbles. There are 3 blue marbles, 4 green marbles, and 5 red marbles. There are totally 12 marbles here in your bag. 3 blue marble, 4 green marble, 5 red marble. There are totally 12 marbles. Now, event A is the event that the first marble is blue. If the first marble is blue, what's probability of B? If the first marble is blue, we remove a blue marble. Then for the second marble, what's the chance of being green? If the first marble is blue and remove a blue marble, what's the level? Is 11 marble. For the second marble, the chance of being green is 4 out of 11. However, if the first marble is not blue, then it's possible that if the first marble is not blue, then it's possible that the first marble could be either green or red. If the first marble is not blue, then it's possible that the first marble could be either green or red. So it's possible that the first bubble could be green. First bubble could be either, if the first bubble is not blue, it could be either green or red. So it's possible that the first bubble could be green. If the first bubble is green, then probability of B. If the first marble is green, we take out one green marble. Then probability of B is 3 out of 11. So you can see that the occurrence of event A affects the occurrence of event B. So here we can see that the occurrence of event A will affect the occurrence of event B. If event A occurs, then event B must be 4 over 11. But if event A doesn't occur, then event B could be 3 over 11. It may still be 4 over 11, but it could be 3 over 11. So the occurrence of event A affects event B. They are dependent events. If the occurrence of one event affects the occurrence of another event, they are dependent events. Next, let me show you a theorem. If A and B are independent events, then probability of A given B is the sense probability of A, and probability of B given A is the sense probability of B. That means if A and B are independent events, occurrence of event B won't affect occurrence of A, and occurrence of event A, it won't affect occurrence of event B. Let's prove it. The proof is simple. For the first equation, probability of A given B can be rewritten as probability of A intersection B over probability of B. Since A and B are independent events, probability of A intersection B can be rewritten as probability of A times probability of B over probability of B. Then we can cancel probability of B. What's left is probability of A. Similarly, for the second equation, probability of B given A, if we use definition of conditional probability, that can be rewritten as probability of A intersection B over probability of A. The denominator is always the condition. Then, since A and B are independent events, probability of A intersection B can be rewritten as probability of A times probability of B over probability of A. Cancel probability of A from top and bottom. We have probability of B. So that's a proof of this theorem. Next, let's look at another theorem. If A and B are independent events, then A complement and B complement, they are also independent events. How do we prove it? In this theorem, we try to show that A complement and B complement, they are independent events. That means we try to show that probability of A complement intersection B complement equal to probability of A complement times probability of B complement. That's how we show two events are independent. So here, let's try to prove this equation. Let me start from the right side. Probability of A complement times probability of B complement. Let me start from the right side. We try to prove this equal to probability of A complement intersection probability of B complement. This equation can be rewritten as 1 minus probability of A times 1 minus probability of B. Because probability of A complement is 1 minus probability of A, and probability of B complement is 1 minus probability of B. Then FOIL, we get 1 minus probability of B minus probability of A plus probability of A times probability of B. Then, since A and B are independent events, This is the same as probability of A intersection B. Since A and B are independent events, so this equation can be rewritten as 1 minus probability of A plus probability of B minus probability of A intersection B. This part can be rewritten as probability of A plus probability of B minus probability of A intersection B. Then this part, probability of A plus probability of B minus probability of A intersection B. This is probability of A union B. 1 minus probability of A union B is probability of A union B complement. 1 minus probability of A union B is probability of A union B complement. If we use De Morgan's law, that can be rewritten as A complement intersection B complement. Since we proved that probability of A complement times probability of B complement equal to probability of A complement intersection B complement, that means they are independent events. So here, since probability of A complement times probability of B complement equal to probability of A complement intersection B complement, then events A complement and B complement, they are independent events.